I'll say, okay, good afternoon, good morning, good evening, depending from where you are. Welcome. It's always nice to see so many names I know and people I know that are attending now. So for today's talk, it's my pleasure to introduce Professor Dimitri Breda from the University of Udine in Italy. So Dimitri is well known for his seminal work on numerical methods for time delay systems, and also for his work in the context of mathematical and computational biology. So he's also founder of the Computational Dynamics, or CD, lab in Udine, which is growing a lot and meanwhile expanding way beyond Udine. So Dimitri has also been very active in our community. In particular, he has been main organizer of a very successful PhD training course in 2019. And very importantly, he will be organizing a new PhD course next year in Udine, which is highly recommended. So at the end of the talk, we will see a bit more about this. So Dimitri, thank you very much for accepting. We're very happy to have you here. And his talk will be about traveling back and forward between finite and infinite dimensional representations. So Dimitri, if you are ready, you have the word.
So good morning, afternoon, or evening to everybody, and thank you, Wim, for the introduction, and of course also Gabor for the invitation. So it is a great pleasure to have the opportunity to contribute to this webinar series, and I have to say that I'm truly grateful to this community first for the constant attention devoted to numerical aspects of time delay systems, at least for what has been my experience in the last 20 years or so. I'm also extremely thankful to and indebted to Rossana Vermiglio and Stefano Vaset for having introduced me to the world of delay during my PhD. And also I'm grateful to very many other friends and colleagues I've met along the way who greatly contributed to the subject. So prior to start, let me note that a complete list of references is appended at the end of these slides, which I'll be glad to make available through the organizers. And if you see me looking down, it's just because I'm using a graphical tablet to annotate the slides in the following. So as we talk about delay, let me start with some background from the past and go back to the 1977 reference monograph by Jack Hale, in which the contribution of control theory to the development of the field is soon acknowledged in the introduction. And a few lines below, Hale records the role of Krasowski in the 50s in, let me read, emphasizing the important fact that some problems for such systems are more meaningful and amenable to solution if one considers the motion in a function space, even though the state variable is a finite dimensional vector. And indeed, Krasowski talks about segments of a trajectory as represented in this original figure, and recognizes the advantages of using the theory of semigroups in understanding their time evolution. And then he sketches what is today known as the Hale-Krasowski notation for the state of a system at time t, which we all denote by x sub t, and it is a function of theta defined as the trajectory at time t plus theta for theta varying in the delay interval minus h0. Here the delay is denoted by h. So the suggestion is that following the evolution of these these segments in time, to follow the evolution of these segments in a space of functions rather than a long time, is much better. And let me illustrate this point of view with a short movie in which you can see the segment evolving a long time, but then it is shifted back into the original delay interval minus tau 0. So here are represented three different dynamical behaviors, namely equilibria, periodic orbits, or aperiodic motion. Okay, let me go back to the slides. Of course, functions are, generically speaking, infinite dimensional objects. And indeed, in another cornerstone monograph on delay equations, Dijkman, Van Gils, Verduin-Lunel, and Walter soon declared that their aim is to study infinite dimensional dynamical systems in the proper mathematical setting, which is the difficult point. And indeed, a few lines below, uncommon symbols like suns and stars appear to validate a variation of constant formula, which is a rather fundamental tool in transferring the stability information from linear to nonlinear equations. Sun-star calculus was developed in the 80s by Clement. Oh, I can use that because of, let me move it. By Clement, Dijkman, and colleagues, in order to provide this switchable mathematical setting, but I will not touch on this level of detail today. So let me start from the linear case, and we consider as a state space the space of continuous functions on the delay interval. And it takes values in Rd, where D is an integer representing the physical dimension of our system, so the number of equations. Tau is a positive number denoting the maximum delay of the system. And this one is the standard nonlinear delay differential equations that we consider. We assume the right-hand side F to be smooth. And of course, X sub T is the state notation that we introduced before. So if we are interested in equilibrium, so zeros of the right-hand side, we proceed through linearization, and we try to plug in an exponential function into our equation, and what we get is the so-called characteristic equation, and we have these very well-known results about the asymptotic stability of the original equilibrium, which states that if all our solutions to the characteristic equation, so what we call the characteristic roots, are in the leftmost part of the complex plane, then our equilibrium is asymptotically stable. So the study of characteristic equations seems fundamental, and perhaps the most celebrated equation is the highest equation, which could or even should be named after Bellman and Wright, and it refers to this differential equation here, which is presented in an unusual form, but its characteristic equation by substituting an exponential comes out to be S to the exponential of S equal A1 times again the exponential AS plus A2. So basically it is of this form here. So in the paper of IS, we find the today well-known distribution of characteristic roots on the complex plane, even though the original illustration refers to this advanced case here, which immediately leads to see the roots through the Lambert W function, and indeed the roots are given by minus the Lambert W function evaluated at minus C. And this Lambert W function is a tool that has been conveniently exploited by several colleagues, for instance, Jarlebring, Ulsoy, and other ones, as you can see in the references. Let me move this annoying part somewhere. Okay. So today about this equation, we practically know everything, and this figure is just one among many others in the literature illustrating stability and bifurcation in the plane of the parameters A and B, at least as far as A and B are real numbers. But if we slightly increase the dimension and go, for instance, to the planar case, we already encounter other difficulties, as emphasized in both Dickman's and Hayes' monographs. And in particular, Hayes seems rather pessimistic, but so far he's completely right, as to call for methods to solve the problem through approximations. And their interest on such methods started to grow rapidly across the century. And from 1977, let me jump to 2001, when during my first year PhD, soon after 9/11, my supervisor sent me to the United States for the first time in my life for my first conference. And at the breakfast of the first morning, my absolute first international contact manifests himself as a rather tall person approaching me by saying something like, "Hello, nice to meet you. My name is Jack Hay." So I said at the time, let's play then. So what you see here are the original transparents of my first talk given at the third IFAC workshop, which was held in Santa Fe, on time delay systems, of course. And as a starting message at that time, there was this somehow threatening warning about not using the characteristic equation to compute the roots. And indeed, characteristic equations are, first of all, difficult to write since they are determinants and possibly ill-conditioned. This is already true for polynomials, and the most famous case is the perfidious polynomials by Wilkinson, which I've been able to trivially extend with this toy system of delay differential equations. And this part here is the Wilkinson polynomial. And for this polynomial and the extended version in delay system, the conditioning number grows unbounded with the degree n, as you can see from the right picture. It is nice to note that the Wilkinson polynomial was wisely used already in the work of Vlidal and Zitek, while initially discussing about their quasi-polynomial mapping-based root finder in 2003. So let's take an alternative viewpoint, and precisely that of the theory of semigroups already mentioned by Krasowski. So the well-posedness of our linear initial value problem lets us define the solution operator, which brings initial functions into the current state at time t. If we collect all these operators as time grows, we get a strongly continuous semigroup whose infinitesimal generator is this operator here, whose action is differentiation, and it is independent of the particular equation we are dealing with. And the only place where our right-hand side, so our model, enters the scene is this boundary condition. As general features, our semigroup is eventually compact, which means that our operator has only point spectrum, so the spectrum contains only eigenvalues, and this is very important because the main result states that these eigenvalues are exactly the characteristic roots we were looking for. Another result states that there is an exponential relation between the spectrum of our generator and the spectrum of the operator. So in the end, what we have on the one hand, a characteristic equation, which is a nonlinear eigenvalue problem, but on a finite dimensional space, which is Rd. On the other hand, we have the spectrum of our generator, which is instead a linear eigenvalue problem, but in infinite dimension. So a starting reference for nonlinear eigenvalue problems, if you are interested, is the survey work of Merman and Voss. And if you are interested in spectral theory for linear operators, I suggest the books of François Châtelain. As already said, at the beginning of this century, the interest in methods to compute the rules started to grow quickly, and several effective approaches have been proposed, like the cluster treatment of Olgach and Sipay, the semi-discretization of Isperger and Stepan, or even the recent studies on multiplicity dominancy by Busada and Niculescu, and very many others which I avoid to list, not to miss any of them. But I guess I'm not wrong by saying that DDE-BIFTOOL is the most used delay software. So let's start by having a quick look inside it. And in the original works of Engelborg and Roos, first the semigroup was discretized via linear multistep methods with a step size h to obtain a matrix whose eigencouples are then corrected by Newton iterations on the characteristic equation. In another work of Engelborg and Roos, also the generator was discretized via incremental ratio by seeing it as the derivative of the semigroup at time 0. And maybe the simplest way to understand this, to understand also the name infinitesimal generator, is perhaps the case of these very simple ordinary differential equations in the reals, whose semigroup all we know to be the exponential a to the power a to the at, and these semigroups depends uniquely on the value of the exponent a. So this is the generator of our semigroup, and a way to recover a is exactly to compute the derivative at time 0. Unfortunately, they choose to discretize this operator by the simple incremental ratio, which has order of convergence 1. So the error decays like power first degree of h. But then Belen and Mazet improved the order of convergence by using higher order Runge-Kutta methods in this work here. But they were looking to time integration and not to stability issues. But today, DDE-BIFTOOL implements also the pseudospectral approach, as nicely described by Kraskop and Sieber in a recent book chapter. So let's have a look at this technique to understand which we recall just the basics of polynomial interpolation. So let us consider a continuous function on an interval domain on the reals. Let's take n+1 distinct points on this domain. And we construct first a restriction operator, which associates to our function the values of the function at our nodes, and also a prolongation operator, which basically does the opposite. So it associates to a vector, a polynomial, which interpolates the components of the vector, and it is represented in the Lagrange basis. By composing restriction and prolongation, we end up with the so-called Lagrange interpolation operator, which associates to a function its interpolating polynomial on the chosen nodes. And then, well, a natural question is what happens if I increase the degree of the polynomial? Is this a good way to approximate a function or not? And in general, the answer is yes. Assume that we operate on smooth functions and we choose good points as zeros of orthogonal polynomials in general R. Specifically, I will use Chebyshev extrema and zeros. And if you want to know about generalities of these kind of techniques, I suggest this book of Rivlin. So what is a pseudospectral method? Based on the previous slide, a pseudospectral method is a way to substitute our unknown function with a vector f, and the way we compute f is based on the interpolation of this vector plus adding some possible initial or boundary conditions given by our problem. And this is one of the many ways to pass from infinite dimension to finite dimension. So we now give an example of application of this technique to compute derivatives of a function at some nodes. And we do this by exactly differentiating our interpolation polynomial at that node. Since both interpolation and differentiation are linear operations, we can express the relation between the components of our function at the nodes with the components of the derivatives approximated at the nodes through this matrix D here, which is called a differentiation matrix, whose entries are simply the derivative of the Lagrange coefficients at the different nodes, and about which I underline these two red blocks here, which we will encounter later on. So to give you an idea what is the advantage of operating with a pseudospectral approach rather than with finite order approaches, I give you this example, which is about an analytic function. And you see that the error for a pseudospectral approach decays very fast. It is a behavior called spectral accuracy, which means that it is an exponential decay of the error in logarithmic scale. And it is very fast compared to a finite order converger. For instance, this is the one given by the approximation of the derivative with the incremental ratio. So let's try to apply this approach to discretize our generator as follows. So I do this in the scalar case for ease of notation. I choose Chebyshev extrema, so including the extrema of the delay interval to discretize the operator. Based on these nodes, I construct the restriction and the prolongation operator as explained before, and I discretize my exact operator here through a matrix or a finite dimensional operator, which is given in this way. So the action, which is differentiation, is obtained by differentiating exactly the interpolating polynomial of my vector and then representing the results into the nodes. All the nodes except the nodes at 0, which is always chosen to be a mesh node, because in 0, instead, we must apply the boundary condition. Of course, our polynomial will not satisfy the boundary condition in general, so we apply the boundary condition to the interpolating polynomial. And this reflects into the final structure of our matrix approximating the generator, which is given here, when you see that the first row depends on the boundary condition, so it depends on the model we are considering, while all the rest of the matrix depends just on the differentiation action, and it is independent of the model. So in my PhD, we could prove that this basic result of convergence, which states that the spectrum of the matrix is correctly approximating the spectrum of the generator in the limit as the degree of the polynomial increases. So this approach has been presented several times since my PhD work. So let me give just a summary of what the advantages and disadvantages are, at least in my opinion, but also following the constructive reactions I collected from this community, noting that in principle, you can use your preferred method to approximate a derivative operator with boundary conditions. So for instance, a disadvantage is the obtained matrix is full, but in general, it has low dimension because the number m of the discretization points we must choose to get desired accuracy is in general low. Of course, a drawback is that it is quite difficult to estimate which is the degree correct to use to get a desired accuracy for spectrally accurate methods in general. But let me mention this very good job of Mikies and Wu, where they discuss a technique to compute all the roots to the right of a certain line in the complex plane by choosing the right value of m. Going on, the pseudospectral approach is able to exploit all the smoothness of the functions we are approximating, and this is one of the advantages because in the back ground, we are approximating the eigenfunctions, which are exponentials in the case of delay equations. And then another drawback is that smaller roots are approximated first, whether we would all like to approximate first rightmost roots for stability reasons. But today, I want to focus on the structure of the generator and on that of its approximation. So the former is a differentiation operator operating on functions satisfying a boundary condition, and the resulting approximating matrix is exactly a differentiation matrix perturbed to impose the discretized condition. And there would be much more to say about this matching and the relation with some star calculus, but of course I had to make a selection. So first, let us broaden our point of view and go beyond the computation of characteristic roots. And let me consider the linear initial value problem originally posed in RD with an initial function phi, and it can be shown to be equivalent to this linear initial value problem, which is instead posed on the state space, which is the function space of continuous functions. And the relation between the two is that u of t, the function evolving in the abstract Cauchy problem, is exactly the state of our system at time t. So basically this one, basically this one is a linear autonomous ordinary differential equation which make evolve functions rather than vectors. And given this point of view, we can have two possible potential extensions. One is to go to linear non-autonomous problems, and the other one to go to nonlinear ones. So let me touch briefly on yet linear but non-autonomous equations. And the question is the following. Is this linear yet non-autonomous problem still equivalent to the linear non-autonomous abstract Cauchy problem? So the answer is probably yes, but I never checked all the details of a possible proof. But independently of this, I have two observations. And the first one is that the domain of this possible generator is time dependent, because now, being the problem non-autonomous, the boundary condition in the domain depends explicitly on time. And this was already nicely underlined by Eric Bucher and colleagues when they were discussing their Chebyshev continuous time approximation method. The second observation is that even if we have this abstract Cauchy problem, surely the information about stability are not in the spectrum of this operator A, because this is already the case for linear periodic ordinary differential equations. Well, going on, now the right-hand side L is non-autonomous. Then because of this, our semigroup is generalized to a two-parameter semigroup, because now also the initial time has a role. And basically, we get what is called an evolution family. And it is just a generalization of the semigroup properties into the two parameters depending case. So among the many methods to approximate, for instance, Fouquet multipliers, this is, I think, the most famous non-autonomous case, the periodic case, I mean. Among all these methods, like the semi-discretization, we proposed the general framework which works for either computing the roots in the autonomous case, the multipliers in the omega periodic case, let me say, and even the Lyapunov exponents for generic non-autonomous problems. And all these three versions depends on a suitable choice of the initial time in our generic evolution operator and the advancing step size h. And the framework is based on separating, on a reformulation which basically separates how the solution of our problem is reconstructing from the initial function, and from, let me say, the information that is given by our equation from one side, and on the other side, how this information is obtained as a fixed point problem. So for instance, in the case of delayed differential equations, like x prime of t equal f of x sub t, the operator v operates in this way. We have our initial function psi, and the solution in the future is given by integrating the derivative. So it's psi at time 0 plus the integral of the derivative, which we call z. And z is exactly what is prescribed by the right-hand side of our equation. And this amounts to the fixed point equation, which is the second ingredient of this reformulation. So let me say this is a very general framework. And in order to get an approximation to the operator formulated in this way, we just have to plug in interpolating polynomials and reduce everything to matrices. I think that the most general version of this approach is the one you can find in the last work of Borgioli and colleagues. It is presented in such a way that it's more an integration method, but it's basically the same thing, but now it is generalized very well to also piecewise discontinuous right-hand side, which is very important in applications. But again, if we deal with problems like this, we have to face the difficulties of dealing with infinite dimension if we try to extend what is known from the finite dimensional case of ODEs. For instance, in the case of Lyapunov exponents, orthogonality is required for both extending the theory and the computation. And indeed, this has to change the proper mathematical setting to which the Dickman monographs was referring to into the introduction. And in this case, we have to move to an Hilbert framework where orthogonality is available. Then the exponents can be obtained from orthogonalizing a fundamental system of solutions and projecting into finite dimension for computational reasons. So you see, we first jump from the finite into the infinite to get the theoretical background. And then we go back to the finite in order to do computations. So this kind of approach for Lyapunov exponents was first proposed in a work with Eric van Vleck in 2014. But I would say, fortunately, today we have a somewhat easier approach, which is this one here. And it is based on how can we use pseudospectral approach to directly approximate nonlinear problems, which was the other way of extending the view of abstract Cauchy problems. Well, about the nonlinear case, I have to say that if the first person I met at my first conference was Jack Hale, well, the second one was Odo Dickman the year later, even if he couldn't know it. Actually, he was giving a plenary talk at the second conference I came, which was held in Vietri sul Mare in 2002, sorry. And roughly after, let me say, 10 years, Odo made a fundamental observation after a talk I was giving on structured population celebrating Mimmo Iannelli in Trento. So it was 2011. So let me go back to the abstract Cauchy problem in the linear case, where discretizing the generator with a matrix corresponds to reduce our abstract Cauchy problems to the finite linear autonomous ODEs represented here. So here the vector evolving has components U0, U1, Um, which represents the approximation of our state at time t at one of the collocation nodes theta I. And of course, if I want to solve these reduced Cauchy problems, now we are in the finite dimensional space, I have also to approximate the initial function, which gives me the vector phi. let me have a look from the PDEs point of view, by which the abstract Cauchy problem is equivalent to the hyperbolic PDE written here. And this can be understood and can be seen by the fact that DDEs basically are transport through the characteristic lines of these equations, which are basically the lines, t plus theta equal constant. And this comes from the fact that the equivalence comes through this function, which corresponds to x at time t plus theta. So the argument is additive. Instead, so you can look at the evolution of the state of your delay equations along this surface here. So as time moves forward, your state is moving in that direction. And what is the pseudospectral collocation approach? Is basically to select a finite number of points of the initial function among the infinitely many ones that compose the initial function, and follow the evolution in time of just these points. So it's what is called the method of lines in the theory of numerical methods for partial differential equations. So, seen in this way, we can extend our approach from the linear case to the nonlinear case by following, let me say, Odo's point of view of delay equations, which are seen as a rule to extend the initial condition beyond its domain of definition. So this is half of the story. So if you are following the evolution of your delay equation, you start from your initial function, and then the delay equation is a way to extend this initial function forward in time. And of course, this rule of extension depends on the particular equation you are dealing with. So this amounts to the first part of the matrix, which is the boundary condition in the domain. And then the other part of the story is to describe the state of your system by shifting it back to the state space. And this action is independent of the equation, and it amounts to these red blocks here. And it amounts, of course, to the differentiation action of the operator. So we can translate our discretized Cauchy problem by separating the shift from the extension and emphasizing so the role of the first equation, which represents the extension, and it is the discretization of the boundary condition describing the domain of the generator, and all the other equations amount for the discretization of the differentiation action of our operator. And they are completely, I repeat, independent of the models we are considering. But now, if you look at our discretized Cauchy problem in this way, you see that if you change your equation, you have to change only the first ODE. And so there are no constraints, and we can extend to linear, from linear to nonlinear. But of course, we need all the ingredients, and in the nonlinear case, which is this one here, we can define again a solution operator which always associates to the initial function of your Cauchy problem the state at time t. Of course, it is a nonlinear operator, but it still has a generator. And this time the generator is still linear in its section because it is always differentiation, but it is nonlinear in the domain, because now the boundary condition is nonlinear due to the nonlinearity of our model. So we have a nonlinear abstract Cauchy problem, but we can discretize it exactly in the same way as before by separating extension and shift. So the only equation affected by our delay differential equation is the first one. And so this opened the doors to easy coding of this problem. And indeed, Davide Liessi, Enrico Santi, and Rossana were able to include this into MatCont, as it was recently presented at the last IFAC meeting in Montreal. So this approach has several good features. For instance, if you are interested in equilibria, there is a one-to-one correspondence between the equilibria of your original delay equation and the equilibria of the approximated ODEs, in the sense that, of course, if x bar is the constant value of your equilibrium function in the state space, then the vector whose components are all equal to x bar is an equilibrium for the reduced ODE. And then, since linearization and collocation commute, we end up with the fact that the eigenvalues of the linearized ODE converge with spectral accuracy to the eigenvalues of the linearized DDE as the degree of collocation increases. Well, today there is plenty of experimental evidence of the spectrally accurate behavior of this approximation, and an example is given with this simple test on the delay logistic equation, which has a non-trivial equilibrium, x bar equal 1. It is asymptotically stable up to the value pi over 2 for the growth parameter, and this is an Hopf bifurcation value. And on the pictures, you can see on the left, the roots calculated with what Odo named the experts pseudospectral approach. And on the right, you see the error in approximating the Hopf value by the, what again Odo called the pragmatic pseudospectral approach. And what is the sense? In the left, we computed the roots by first linearizing the DDE and then discretizing the generator to get the eigenvalues. And this, of course, requires you to linearize, which is easy in the case of the logistic equation, but it is not always so. And then you have to discretize the operator with boundary conditions and whatever. So that's the adjective expert. On the other hand, we have this pragmatic approach, which simply lets you discretize the DDE directly with a system of ordinary differential equations. And then you don't have no more worries, because there are a lot of tools available to treat ordinary differential equations. And for instance, in this case, we computed the bifurcation value by using MatCont. So that's why it is pragmatic as an approach. You get the ODE, and then you use your favorite tools to analyze ODEs, continuation tools or whatever. So this is the point of view of reducing the ODEs and then using available tools. And if you want to know more about this, you can surely ask Francesca Scarabell and other people at CD Lab who greatly extended and improved this line. I think I have not much time today to mention properly all the possible extensions, but please, if you're interested, have a look at the lab homepage. And of course, I'd like to thank all the members of CD Lab who actually have a face, as you can see here, and they have done and still are doing wonderful works in several directions. And these are Alessandro, Simone De Reggi, Davide Liessi, Stefano Maset, and now Alessandro Pecile and Enrico Santi, Francesca Scarabell, and last but not least, of course, Rossana Vermiglio. So let me just give a brief mention to what kind of difficulties you can encounter if you try to extend these approaches to different classes of functional equations. because the point is that the evolution structure given by the semigroup of solution operator and this generator is somehow universal to many classes of dynamical systems. So if you can exploit this structure, you can obtain similar results. And for instance, the differences with another celebrated classes of functional equation, which is the one of renewal equations, is based on the different state space, which typically is the space of integrable functions, or L1 functions. And the other main difference is that since our equation prescribes not more the derivative, but the solution itself, this affects, of course, the boundary condition in the domain. Well, these equations are very well known in population dynamics. And indeed, they were originally proposed by Kermack and McKendrick in 1927. And this is a paper where the SIR model of ODEs was just a particular instance obtained under specific assumptions. So their work was really much, much more general, and it was about integral equations. So, of course, the main differences I highlighted are the source of many difficulties for extending the approaches I presented. And the main reasons are, for instance, that the tools you use in spaces of L1 functions are not the same that you are used to use for continuous functions. So you have to pay a lot of attention. Of course, I do not have the time to go through all the works from the members of the CD lab, but at least I leave you this rough guide in this single slide. And let me comment just to underline once more the interplay between the infinite and the finite, that, for instance, Alessia Ando has been able to prove the convergence of collocation to compute periodic solution of delay equation, which is the method that everybody used with DDE-BIFTOOL by imposing, this was possible by imposing the periodic boundary condition to the state in the infinite dimensional state space and not to the function values at the period extrema. Similar difficulties have been encountered by David Elias in proving the validity of a Fouquet theory for renewal equations. So let me go towards the end, and as just a last remark, let me change completely point of view. Since so far, everything was based on the assumption that we have a model at disposal, perhaps coming from first principles. But the recent explosion of data science is inverting this direction somehow, and tools start to be available to recover governing equations from a time series of data or of snapshots. So recently I had the opportunity to experiment some preliminary work in this direction, thanks to my student Alessandro Pecile, and also to the collaboration with people at CISA. And some of the results we obtain seem rather promising in recognizing at least both the right coefficient in our unknown equation. So these are examples about a specific case of the Mackey-Glass equation. So these data were obtained just knowing the time series of a simulation without knowing the model behind. And these techniques were surprisingly good also to get the correct value of the delay, which was 1 in the experiments. And also, together with the delay, also the right value of some important parameters in the model. Of course, this is a subject of another talk, and I presented some preliminary results in Montreal, so I'm not going to discuss about this interesting topic. But if it happens that you get interested, let me mention some announcements. So next summer in June, there will be this Dobbiaco Summer School in Italy, in the Dolomites. So it's a very good place to be in the summer. And it will be about data-driven methods for the computational sciences. It is organized by the University of Trieste, and I have to add, this is just a cut from the website, the University of Udine, the University of Innsbruck, and also with the help of CISA in Trieste. The lecturers will be Nathan Kutz and Carsten Urban, which are two experts in these new areas of data-driven methods. And as Wim already mentioned it in the introduction of this seminar, let me once more advertise this PhD school, which will be given next year in November at the Center for International Mechanical Sciences. So this is organized in collaboration with Janon Wu, and here you can see the list of lecturers, among which you can see also Odo Dickman, and I think also other ones are in the audience today, like Francesca and Rosanna and Davide. And on the right, you can see a picture of the cover of the Springer volume of the lecture notes from the previous school, which was held in 2019. And in red, you can see the list of the lecturers at those time, among which also Wim and Tamas were. So this volume was published a couple of months ago, so now it is available. Last, let me mention a call. If you know someone who wants to join the CD Lab through a postdoc, one-year position about epidemiological models and numerical methods for structure population. It will be open till January next year. And finally, let me share a couple of quick considerations about all I presented today. So the title mentioned back and forth between the infinite and the finite. I think that this is quite important for both the practice, in which usually the direction is to go from the infinite to the finite. And so here the typical questions are, for instance, how many equations do I have to use in order to get the desired accuracy in the results? Or how large must be M in order to get accurate approximation to the roots, to the multipliers, or to whatever object you are interested in? But it is not only important for the practice. It is important also, in my opinion, for the theory. And now the direction is the opposite one, because you go to the finite, from the finite to the infinite. And the big question is, what happens now if you push your degree of discretization to the limit? So what if M goes unbounded to infinity? So these are typical questions, but there is an even bigger question, and it is, where do we find, or where can we find answer to the previous questions? So let me go back to this monograph from Odo and colleagues, which mention in the title several kinds of analysis, like functional, complex, and of course, nonlinear analysis. And definitely this was, and still is, and will be always a great, great, great contribution to our field. And beside this, I put just a less important contribution, but which is about another analysis. It is about numerical analysis. So to answer the question before, I would like to draw your attention to the link, to a possible link between numerical analysis and all these other kind of analysis. And it is maybe the place where we can try to find answers to our question. And this is basically the approximation theory. Specifically of functions, of course. For instance, we all know about the subject if we deal with continuous functions. But if we start dealing with bounded variation functions, absolutely continuous function, L1 functions, or we deal, for instance, with unbounded domains, then all the classical tools of interpolation or approximation are not at least complete, if not available at all. So that's all, and let me thank you very much for listening.
Okay, Dimitri, thank you very much for this very clear and didactic presentation.